In lesson 1, when we did introduction to sequences and series, I had mentioned that in grade 12 we study only 3 types of sequences, and we already have completed 2 of them so far: arithmetic sequence and quadratic sequence. Lesson 3 will be looking at studying the geometric sequence. To better understand a geometric sequence, suppose that we have term 1, which we call T1, or we write as T1, and we say that this term is given by some number A, similar to how we did an arithmetic sequence. However, for us to go to term 2, we then say that we multiply term 1 by some number R, so that now I'm going to have the A here times the R. That means I'm going to have A multiplied by R, which will give me AR, and that would be our second term. So that means our T2 would then be A times R. We further go on to do term 3 by multiplying by the same number R, so that now I'm taking this AR and multiplying it by an R. Now this would mean that I will have AR times the R, and this would give me A. Remember here I'm going to keep the base and add the exponents, our rules of exponents. We keep the base and we add the exponents. We have invisible 1 here and invisible 1 here. That means we have 1 plus 1, and that will give us a 2. So this would then mean that our second term will be defined by AR. Our third term, remember when we multiply by R here, we get the next term here, which will be AR to the power 2. And we're saying that this is term 3. And we can continue doing the same operation, so that we multiply by the same constant number R. And now we have here AR squared, which is term 3. Then we're multiplying it by an R. You multiply this by R. And now we're going to have A. And again here I keep the base and add the exponents. Remember that I have an invisible 1 here. It will mean that I'll have a 2 plus a 1. That should give me a 3. So I'll have A R to the power 3. And that actually gives me the fourth term of the sequence. So the term that will come here would be AR to the power 3, and is actually the fourth term. Now this sequence can be increased in that same way by multiplying by R. We can continue doing the same pattern here to get term 5, term 4, and so on, by multiplying by the same number R. The fact that we're multiplying by R would mean that if I take term 2 and divide by term 1, that means I'm going to have here term 2, which is this, is going to be AR, and I'll divide by the A there, which is going to be the A. And this would then mean that the A and the A would cancel each other, so that I'm only left with an R. The same can be said to say if I take term 3 and divide by term 2, this would mean that I'm going to have my term 3 to be AR squared, and we're dividing that by term 2, which is just AR. Now this would mean that the A here would cancel each other, and now I have R squared divided by R. So this will narrow down to us using the laws of exponents, where we say we keep the base and we subtract the exponents. I'm going to have 2 minus 1, and this would give me an R. if we do the same operation, we divide T4 by T3, you'll find that you get the R as well. Now, what this means is that we then have the same number R, right, when we divide. So this would make sense because multiplication and division are reverse processes. So if I multiply it by R going in that direction, then if I go in the reverse direction by dividing these successive terms, I should also get the same R. For that reason, we then say that R is actually a common ratio. Remember, a ratio is a number that you get when you divide numbers. So because this R we can find it by dividing successive terms, we call it a ratio. But also it's not just a ratio, it's a common ratio. Remember, to say something is common, it means that it is constant, it does not change. So we get the same number R, and then that's why we call it the common ratio. But again, let's zoom in into the pattern that is happening in this sequencing, because there's clearly a pattern. If you look at A, it appears in all the terms. We have A in term 1, we have A in term 2, we also have A in term 3, and it appears in term 4. This means that if the pattern were to continue to term 5, I will still have A, and if it continues to term 6, I'll still have A, and so on. A seems to be a number that appears. However, the A seems to come out multiplying the R here, an exponent of R. In term 2, it appears as an exponent of R to the power 1. In term 3, it appears as an exponent of R to the power 2. And in term 4, it appears as an exponent of R to the power 3. But note that in term 1, we actually don't have R at all. It doesn't appear at all. Now, this pattern looks familiar. We've seen it before in an arithmetic sequence, except that it was not in an exponent form. It was actually occurring as a linear form. So here, the pattern that we see is that if we have 1 here as an exponent, the number of terms is 2. If we have 2 as an exponent, the number of terms is a 3. If we have a 3 as an exponent, the number of terms is a 4. This means that if I were to have an exponent as a 4 in the next term, that means this will be T5. So this is to say that we see the relationship where the exponent here is actually 1 less the number of terms. How do I mean? I mean that if you want to get this exponent here, you would take the number of terms, which is a 2, and you subtract 1. It is 1 less. Then this would mean that I will have 2 minus 1, which is a 1. If I say 3 minus a 1, the number of terms, which is a 3, and then I subtract 1, I then get the 2. It is 1 less. It's a pattern that we see there. But now the question would be, what actually transpired in term 1 for us not to have an R? Well, the best way of looking at this would be for us to say that, let's say term 1 was A R to the power 1 minus 1. Now I'm saying 1 minus 1 because remember our pattern is such that we're saying term 1 would be given by, if we're looking at the exponent, it will be the number of terms, which is the 1. So this one here, and we subtract 1 because we're saying the number of terms should be 1. The exponent here should be 1 less the number of terms. So I'm taking the number of terms and I'm reducing it by 1 so that it is 1 less the number of terms. Now, if we do that, we can see that here we're going to have AR to the power 0. And we all know now from our laws of exponents that any number raised to 0 is actually going to be a 1. So what we have here, we have A times 1. And all of us know that any number multiplied by 1 is actually that number. And that's the reason why here the first term will be given by A. So here actually the R is there, but it's an invisible R because the R is given by 1 minus 1. And in term 2, definitely we are going to have A r to the power 2 minus 1, because we are saying here that the number of terms is 2 because we are on term 2, and we subtract 1 because it is 1 less. Now if we simplify this, we're going to have an a r to the power 1. That's why term 2 actually is given by ar. To get term 3, we're going to do the same thing to say we have an a r to the power 3 because we are on term 3, the number of terms, right, minus 1. The number of terms minus 1. The exponent here at the top should be the 1 less the number of terms. So we're taking the number of terms and we're subtracting 1. And this will simplify down to be r to the power 2 because 3 minus 1 is a 2. And this then becomes term 2. This then becomes term 3, sorry. That's why term 3 we have ar squared. Then if you were to do term 4, the same mathematics will apply. You will have ar to the power 4 because we are on term 4 minus 1 because it's the number of terms is 1. The exponent here is 1 less the number of terms. So that now we have ar to the power 3. And this is what is given as term 4 there. So now, just to extend this pattern, suppose that as we go on in looking at the larger number of terms in future on this sequence here, let's say we have a term, I would say 50 for instance. I'm just picking an example out of my head. Now it means this would be given by an a, because we have an a always in the sequence, but this a multiplies an r. And we just said that the pattern that we see here is that the exponent would be 1 less the number of terms. In other words, we are going to say this number of terms, which is 50 minus 1, and that should give us 49. So it means term 50 should be given by a times r to the power 49. It's a pattern that we see happening in a geometric sequence. And of course, we also spoke in lesson 1 when we did introduction to sequences and series that if the sequence continues, there's a point where we can define it as Tn, and we call this Tn the nth term. And we said it represents any term in the sequence. This would imply that the nth term here, if we were to define it, it will be given by the first term a, and we multiply that by r. Remember, we already know that the first term appears all the time in all the terms. Then we're going to multiply that by the r. But in this case, we are going to say n, which is the number of terms minus 1. Because we have been saying, or we have observed the pattern that the exponent here is always 1 less the number of terms. In other words, the number of terms reduced by 1. Then this then becomes a general way of defining any term in this sequence, in a geometric sequence, so to speak. Now, to conclude what we have said, I will then run through these terms as we have seen them. We said T1 is given by some number A, we called it A. And we're saying here that T2 will then be given by the A multiplied by R, because here we have to have the exponent has to be 1 less than number of terms. And in fact here we also have the exponent being 1 less than number of terms because it is r minus 1, which actually is r to the power 0, and any number raised to 0 will simply be 1. That's why we have a alone. Then if we have term 3 here is going to be given by a r to the power 2, because we're saying 3 minus 1, we get the 2 there. Term 4 will also be given by a r to the power 3. I think you can see the pattern now. Now this means that if I were to continue this sequence and perhaps get to some term here, 11, this would be a r to the power 10, because we're simply going to say 11 minus 1, which is a 10, and this will define the 11th term. The sequence can continue growing in this manner to to a point where we get maybe to term 52, this will be given by AR to the power 51, because 52 minus 1 would give us the 51. Now this pattern can continue going on like that. I'm going to use this space here at the bottom to say it will get to a point where we get to Tn, the nth term, and we're saying it's going to be defined by AR to the power n minus 1, because we're saying here the number of terms minus 1 here is always 1 less the number of terms. And we're saying that Tn is the nth term, and in this case, if you look at this statement here, it then becomes actually a formula. In other words, this nth term, the Tn, is the same as a formula that defines any term in the sequence. So here, I'm just going to write the statement to say the nth term, which is Tn, is actually the general formula, meaning it's a formula that can assist us to find any term in the sequence. So for instance, if I were, let me use this space here. If I were to take the formula Tn r to the power n minus 1, and I were to look for term 1, in other words, I'm going to have my n to be equal to 1 because I'm looking for term 1. That would mean that I'm going to have a r to the power 1 minus 1, and this will give me a, r to the power 0, which actually would be a, because r to the power 0 is just a 1. And that is exactly what we found for term 1. So we can find any term using the formula because it's a general formula. You can try this with term 2 as well. That means I'm going to have T2 is equals to a r to the power 2 minus 1. Now all I've done is that I've substituted the 2 here on the n and the 2 here on the n, and clearly this should be obvious that we're going to have a to the power r, and that's how we defined term 2. I can take any term. Let's say we take this 52 term. This would mean that I'm going to have T52. Alright, this is the value of n here, because we're looking at the 52nd term, which will be given by a, which is this here. Then we're going to have r to the power n minus 1, but our n we're saying here is 52 minus 1. And this actually will give us a to the power 52 minus 1 is indeed 51. And that's how we defined that when we were studying the pattern that is taking place in this sequence. So this becomes a formula to determine or find any term in the sequence. The other thing that we have to look at is that if you recall an exponential function, you would remember that it is given by the formula y is equals to ab to the power x, and we'll normally write plus or minus p here. And if you look at the general formula for this sequence, is given by Tn is equals to AR to the power n minus 1. Now, there's a lot of similarities between these two equations. The Tn here has the same properties as y there. And the A here has the same properties as the A in that other equation. The B here would be the R, and the X here would be the n minus 1. And in this equation, we can see that we are adding 0 here. So the P is actually 0. That's why here it doesn't appear. So this means that this, remember, we call it an exponential equation, right? We called this an exponential equation or function when we were studying exponential functions or looking at the exponential form. And of course, this is a formula for a geometric sequence, this one here. Now, for that reason, sometimes a geometric sequence is actually called an exponential sequence. So sometimes if you hear someone saying that geometric sequence is actually the same as saying exponential sequence, because this sequence has the same formula as that of an exponential equation or function. So this means these terms here that we have studied, the terms in this sequence, they're actually exponential. In other words, they are growing at an exponential rate. And actually that makes sense, because if you multiply by r and multiply by r, you can see that these terms are actually growing faster. They're not linear as opposed to an arithmetic sequence. Now, as a conclusion, we will then say that a geometric sequence is a sequence with the following properties. It has the following properties. One, we have a common ratio, which is defined indeed by r is equals to tn plus 1 all over tn. Remember, tn plus 1, we said that it is the next term, and we said that tn is actually the previous term. So we're saying here that if you take the next term, you divide by the previous term, you should get a constant ratio. So for instance, if I say n is actually equals to 1, this means in this formula, we're going to have r is equals to t1 plus 1 over t1, because now I'm putting the 1 here in place of n, because we're saying n is equals to 1. And this would mean that I'm going to have here t2 divided by t1. And we spoke about this to say term 2 divided by term 1 will give you r, which we said is a common ratio. We spoke about this. You can do the same to get t3 divided by t2 by actually making n to be 2. So if we say n is equals to 2, then we have r is equals to t2 plus 1. So now I'm saying here the n is a 2 here, so I'm going to have a 2 plus 1, not minus. Here is a 2 plus 1. We're dividing here by t2 because we are saying that the n is a 2. Now this will say that we have term 3 divided by term 2. So actually this becomes a general formula for finding the common ratio. Remember lesson 1 where we defined tn plus 1 to be the next term and tn, the nth term, to be the previous term. To close this introduction to geometric sequences, I'm going to just look at an example of a geometric sequence. Say, for example, our first term in a geometric sequence is given by 1 over 2. Then we multiply here by a 2 to get to the next term. That means I'm going to have 1 over 2 times 2, the 22 would cancel, then I'm going to have the next term as 1. Then to get to the next term, I then multiply again by the 2 because the common ratio is the same number that we use to extend the sequence. If you multiply the 1 by a 2, we indeed should get a 2 there. Now to get to the next term, I multiply by 2 again, and then if we say 2 times 2, we should get a 4. And I can grow this sequence multiplying by 2 until we go to infinity. Hence, maybe we can call this an infinite sequence because it continues with those 3 dots. It says that it continues until infinity. Now, if you were to be given this sequence, if you are looking for this number here, you can say 1 divided by 1 over 2, you should get the 2. You can say 2 divided by 1, you should get the 2. You can say 4 divided by 2, you get the 2. That's how you get your common ratio, r. Is the ratio between consecutive terms of this sequence. Stay tuned for the practice questions on this sequence.